Welcome back. In this section, we're going to be looking at some applications of the derivative when it comes to exponential functions, and then we're also going to start looking at integration with exponential functions. So all that stuff that we did in chapter 3, finding increasing and decreasing and concave up and concave down and extrema and all the rest, that now can apply to exponential functions as well. And I've got this function here, and I'm looking to find all the relative extrema, figure out what kind of extrema it is, and I've left it open as to how I want to do that. The classifying, maybe I might use first derivative test, maybe I'll use second derivative test. We'll figure that out as we go. One thing that I'm thinking to do for myself personally, if you like this function as it is, you certainly can keep it that way. But I feel like I will probably wind up losing negatives somewhere along the way, especially if I have this e to the minus x. I know when I differentiate it, I'll have a e to the minus x times a minus 1. And I know for myself, my habits are such that I tend to drop negatives or lose them along the way when there's several steps in play. So one thing I could potentially do might be to rewrite this function. I won't be able to rewrite it so that it's no longer a quotient, but if I were to multiply top and bottom by e to the x, then on the top I'd have 2e to the x. E to the x times itself would be e to the 2x, and e to the minus x times e to the x would just be 1. So I'll still have something where when I differentiate it, I'll have 2 in front, but I have a much better chance of remembering the 2 in front than remembering the negative or not losing it along the way. So when I find my derivative for this function, I'm actually going to not differentiate the original version of it. I'm going to differentiate this version. You'll get the same results if you differentiated this version. It'll look different, but it'll have the same meaning. Okay, so let's do our derivative, and this is a quotient, so I guess quotient rule is what's happening for us. The bottom is going to get squared, and then the bottom will come up, times the derivative of the top. Derivative of 2e to the x would just be 2 times e to the x. And then minus the top as it is, times the derivative of the bottom. And the derivative for the bottom, derivative of e to the 2x, well, that's itself, times derivative of 2x, which is 2. And the derivative of 1 is just 0. And now we can see that I've got e to the 2e to the x rather. That's a factor in both of those terms. So 2e to the x I can take out, leaving an e to the 2x plus 1 from the first term and a minus 2e to the 2x from the second term. And if I wanted to do one little last bit of cleaning up here, I could say this is 2e to the x multiplied by 1 minus e to the 2x over e to the 2x plus 1, whole thing squared. Okay, so I've got my first derivative. So now when I'm thinking about critical numbers, remember for critical numbers we need to figure out any place where either the derivative is 0 or the derivative is undefined. So for sure the derivative will never be undefined, and the reason for that is this denominator will never be 0. E to the 2x, no matter what e to the 2x is, it's going to be something bigger than 0. So e to the 2x plus 1 will definitely be something bigger than 1, and when we square it, it'll still be something bigger than 1. So our denominator is never 0. I don't have to worry about this fraction here ever being undefined. So I only have to worry about when the derivative is equal to 0 then, and the derivative is equal to 0 only happens when the numerator for this thing is equal to 0. And for that, if the numerator was equal to 0, then you'd have two little mini equations to solve. And one of them would have no solutions. So we would have 2e to the x times 1 minus e to the 2x. That would be equal to 0, which means either 2 to the e to the x is 0, or 1 minus e to the 2x is 0. 2e to the x is 0. This has no solutions. And that's because e is always going to be something greater than 0, e to the x rather. So 2e to the x will definitely also be something greater than 0. It'll never be equal to 0. The other equation, on the other hand, 1 minus e to the 2x, that's going to definitely be equal to 0 somewhere. That'll be where 1 is equal to e to the 2x, or where natural log of 1 is equal to where natural log of 1 is equal to 2x. Now, of course, natural log of 1, that's just 0. So in other words, where 2x is 0 or where x is 0. That's our only critical number that we've got on this function. If we're thinking about where this is as a point, when x is 0, the y value would be 2e to the 0, which is 1, over e to the 0, which is 1 plus 1, or in other words, we would have the y value is 1 when x is 0. Okay, so that's the first part of our job done. We have our derivative. We have figured out where the critical numbers are. As far as classifying extrema goes, we have first derivative test or second derivative test that we can use. For this one, I really feel like the second derivative test is a bad choice because for the second derivative, it would be a nasty quotient with a product inside of it. I have zero desire to find the second derivative of this function. As far as first derivatives go, it's actually not that bad because if we're taking a look at this, no matter what we put in for our first derivative, the denominator for sure is always going to be positive because it's a perfect square. And this first little factor, 2e to the x, will also always be positive. So when it comes down to evaluating the first derivative and figuring out if it's positive or negative, I really only need to care about this bracket, 1 minus e to the 2x. Depending on whether that bracket is positive or negative will tell whether the entire thing is positive or negative. Also, I only have one critical number, so I just need to figure out what's going on with my derivative on either side of 0. So for that, I can pick any x value I feel like picking, and so I'll go with -1. And if I'm looking at f prime of the derivative rather, at -1, we'll find that the derivative happens to be increasing. The derivative rather happens to be positive, which means our function is increasing. And you can see that if we go back to our derivative, the 2e to the x is positive when x is any value. The denominator is always positive for any value. And if we put in -1 for x, if you'd had 1 minus e to the -2, that turns out to also be positive, which means our derivative is positive, so we are increasing. And similarly, if we're thinking about it, x is equal to +1. At +1, 2e to the x is always positive. The denominator is always positive. And for this bracket, when x is 1, you'd have 1 minus e to the 2, which is something negative. Positive times negative divided by a positive would be something negative. So our derivative is definitely going to be negative, which means that we are decreasing. So that means we can say that we have a relative max at the point 0, 1. All right, so now that we know the derivative of e to the power of x, I mean, it's kind of obvious what an antiderivative of e to the power of x would also be. So now we have our integration rule for exponential functions. If we know that e to the x is the derivative of e to the x, then e to the x is also an antiderivative of e to the x. Of course, because we also know it's not just going to be e to the x, it's going to be usually e to some function of x. That means we're often going to wind up needing to do some sort of substitution to get our way through the problem. So let's take a look at this first problem. We have e to the 7x minus 2 that we want to find an indefinite integral of. And if I were to just let u be that exponent, 7x minus 2, then I know that du, the differential, would be the derivative of that times the differential for x. So du is 7 dx. And I can modify it so that I have replacements for everything in my original indefinite integral. I know that e to the 7x minus 2, that'll be replaced with e to the u. And dx, my differential, that's replaced with 1/7 du. And then now I just have to find my antiderivative and then go backwards. So I have 1/7 e to the u, which is 1/7 e to the 7x minus 2, plus constant c. All right, so let's do some more while we're at it. So I've got another one here where there's an exponential function, and if we're taking a look at our exponential function, we can see that I have a secant in the numerator, well, specifically a 5 secant in the numerator, and I've got outside of that exponential function a secant times tangent. So if we're thinking about things in terms of functions and their derivatives, I can see that I've got something close to that going on. So I already know that I'm going to be making a substitution, and I kind of have the idea of what the substitution is that I'm going to be doing. So, all right, let's take a look at doing a substitution with letting u be 5 secant of x. So du is 5 secant x tangent x dx. And then I can now say, well, that means that 1/5 du is secant x tangent x dx. And so now I can clean things up and rewrite things all in terms of u. The e to the 5 secant x is now e to the u. And the secant x, tangent x, and dx, all of that is being replaced with 1/5 du. And now we kind of know what we're going to get. We're going to get 1/5 e to the u, which is 1/5 e to the 5 secant of x, plus our constant c. So again, we're always sort of on the lookout for things when we're looking at any sort of an integrand. Is there some way I can clean this up? Is there somebody whose derivative is also present? And I can definitely see that going on here. I see there's an e to the x and there's another e to the x, and I know e to the x is its own derivative. And actually even more, e to the x plus 2, its derivative is e to the x. So I'm feeling like that's another place where maybe I need to do a substitution. I'll say let u be e to the x plus 2. And so that means my differential du is just the derivative, which is e to the x times dx. And I have a replacement for everybody. The e to the x plus 2 in the denominator is now a u in the denominator, and an e to the x dx, that's being replaced with du. So I've got myself 1 over u du, and I know that that should be natural log of absolute value of u plus c. So this is natural log of, then, u is e to the x plus 2. So natural log of e to the x plus 2 plus c. This is another one of those ones where I can dispense with the absolute value, actually. If we're taking a look at this, I know that e to the x is always bigger than 0, and so e to the x plus 2 should always be larger than 2. So actually there's no worry about the inside ever being negative. That's not possible, so the absolute values aren't really needed anymore.